In earlier class, we learnt polynomials, degree, terms and classification based on that degree and number of terms. Consider the polynomial p of x is equal to x square minus 3x minus 4. Now, let us determine its value at x is equal to minus 1. Substituting x is equal to minus 1 in the given equation, we get p of minus 1 is equal to 0. Here, minus 1 is called the zero or root of the polynomial p of x. In general, a real number k is said to be a zero of the polynomial p of x if p of k is equal to 0. Why are zeros of a polynomial important? Roots or zeros are important because they are solution to the polynomial equation p of x is equal to 0. They also help us to determine a certain relationship that exists between zeros and coefficients of a polynomial. Consider a linear polynomial 2x minus 5. Plot graph of y is equal to 2x minus 5 by computing values of y for different values of x and tabulating the values obtained. How do you interpret the graph obtained? We see that the graph for this linear polynomial is a straight line that intersects the x-axis midway between x is equal to 2 and x is equal to 3, that is, at the point 5 by 2, 0. Mathematically, the zero of the polynomial can be found by solving the equation 2x minus 5 is equal to 0. Solving this, we get x is equal to 5 by 2, which is the zero of the polynomial. What do you infer from this? Thus, the zero of the polynomial 2x minus 5 is the x-coordinate of the point where the graph of y is equal to 2x minus 5 intersects the x-axis. In general, for a linear polynomial ax plus b, a not equal to 0, the graph is a straight line which intersects the x-axis at exactly one point minus b by a, 0. It has exactly one zero, namely the x-coordinate of the point where the graph of y is equal to ax plus b intersects the x-axis. This is the geometrical interpretation of the zero of the polynomial. Consider a quadratic polynomial x square minus 2x minus 3. Now, let us see what the graph of y is equal to x square minus 2x minus 3 looks like. Compute values of y corresponding to a few values of x. Tabulate the values and plot the points on a graph. How do you interpret the graph to obtain the zeros? We observe from the graph that 3 and minus 1 are the x-coordinates of the points where the graph of y is equal to x square minus 2x minus 3 intersects the x-axis. These are the zeros of the quadratic polynomial. In fact, for any quadratic polynomial ax square plus bx plus c, where a not equal to 0 are precisely the x-coordinates of the points, where the parabola represents y is equal to ax square plus bx plus c intersects the x-axis. In the earlier example, we saw that for any quadratic polynomial ax square plus bx plus c, where a not equal to 0, the zeros are precisely the x-coordinates of the point where the parabola representing y is equal to ax square plus bx plus c intersects the x-axis. Now, observe the parabolic graphs of a quadratic polynomial. The graph cuts the x-axis at two distinct points but starts lower than x-axis. The graph cuts x-axis at only one point. The graph does not cut the x-axis at any point. The graph of the inverted parabola cuts the x-axis at only one point. The parabolic graph formed by a quadratic polynomial ax squared plus bx plus c can either shoot upwards or downwards depending on whether a is greater than 0 or a is less than 0. Now, take a closer look at the quadratic graph that cuts x-axis at two distinct points. Identify the zeros of the polynomial for the given graph. We observe that the parabola opens upwards or downwards and cuts the x-axis at two distinct points of the given graph. The x-coordinates of a and a dash are the two zeros of the quadratic polynomial ax squared plus bx plus c. Now, take a look at the quadratic graph that cuts the x-axis at exactly one point, that is, at two coincident points. How many zeros does this graph have? Here, 2 points A and A dash coincide to become one point A. So, the x-coordinate of A is only 0 for the quadratic polynomial ax squared plus bx plus c. Now, observe the graph of the quadratic polynomial, which is either completely above or completely below the x-axis. Do you find any zeros for this polynomial? No, since the graph does not cut the x-axis at any point, the quadratic polynomial ax squared plus bx plus c has no zero. So, from all the above graphs, we can geometrically see that a quadratic polynomial can have either two distinct zeros or two equal zeros, that is, one zero or no zero. This means that a polynomial of degree 2 has almost two zeros. Now, let us consider a cubic polynomial x cubed minus x squared minus 6x. Can you guess what will be the shape of the graph of a cubic polynomial? A cubic polynomial is of the form ax cubed plus bx squared plus cx plus d, and since the degree is 3, it will cut the x-axis at 3 points. Now, let us check if this is correct by drawing the graph of y is equal to x cubed minus x squared minus 6x by listing values of y corresponding to a few values of x. From the graph, we observe that minus 2, 0, 3 are the x-coordinates of the only points where the graph of y is equal to x cubed minus x squared minus 6x intersects the x-axis. So, these are the zeros of the polynomial. Thus, a cubic polynomial of the form ax cubed plus bx squared plus cx plus d, where d not equal to 0, has at most 3 zeros. In general, given a polynomial p of x of degree n, the graph of y is equal to p of x intersects the x-axis at most n points. So, a polynomial of degree n has at most n zeros. Have you observed any relation between the zeros and the coefficients of a linear polynomial? Let us first look at a linear polynomial 2x plus 4. The zero of the polynomial is minus 2, which is the same value that we obtained graphically. This equation of the form ax plus b, whose zero is minus b by a. In general, if k is a zero of p of x that is equal to ax plus b, then p of x is equal to ak plus b that is equal to 0, gives us 2k plus 3 which is equal to 0, that is, k is equal to minus b by a. So, the zero of the linear polynomial ax plus b is minus b by a, that is equal to minus constant term divided by coefficient of x. Thus, the zero of a linear polynomial is related to its coefficients. Now, let us take a quadratic polynomial 2x squared plus 5x minus 3. Can you find the relationship between the zeros and the coefficients of a quadratic polynomial? In our earlier classes, we have learned to factorize a quadratic polynomial by splitting the middle term. Here, we need to split the middle term 5x as the sum of two terms, whose product is 2 into 2 into 3, which is equal to 6x square. So, we write 2x square plus 5x minus 3, which is equal to 2x square plus 6x minus 3, that is equal to 0. 2x into x plus 3 minus 1 into x plus 3 equals 0, which is equal to 2x minus 1 into x plus 3, which is equal to 0. So, the values of p of x is equal to 2x square plus 5x minus 3 is 0 when 2x minus 1 is equal to 0 or x plus 3 is equal to 0. That is, when x is equal to half or x is equal to minus 3. So, the zeros of 2x square plus px minus 3 are half and minus 3. Calculating the sum and product of zeros, we get sum of zeros is equal to minus 3 plus half, that is equal to minus 5 by 2, which is nothing but the ratio of the negative coefficient of x by coefficient of x square. Product of zeros is equal to minus 3 into half, that is equal to minus 3 by 2, which is the ratio of the constant term by coefficient of x square. We can arrive at a generalized statement by comparing it with a standard form of a quadratic equation. In general, if alpha and beta are the zeros of the quadratic polynomial ax square plus bx plus c, where a is not equal to 0, then alpha plus beta is equal to minus b by a and alpha into beta is equal to c by a. This is the relationship of the zeros with the coefficients of a quadratic polynomial. Let us take a cubic polynomial 2x cubed plus x square minus 5x plus 2. Observe the graph obtained by plotting the listed values of y for different values of x. From the graph, we see that the zeros of the polynomial are the x-coordinates where the curve crosses the x-axis, that is, at points half, 1 and minus 2. Taking the sum of zeros, we get sum of zeros is equal to minus 1 by 2, which is nothing but the ratio of negative coefficient of x to the coefficient of x square. Similarly, the product of zeros is equal to minus 1, which is expressed as the ratio of negative of constant term to the coefficient of x cubed. Taking the sum of the product of zeros taken two at a time, we get the sum of product of zeros is equal to minus 5 by 2. This is expressed as the ratio of the coefficient of x to the coefficient of x cubed. We can arrive at a generalized statement by comparing it with a standard form of cubic polynomial. In general, if alpha and beta and gamma are the zeros of the cubic polynomial ax cubed plus bx square plus cx plus d, where a is not equal to 0, then alpha plus beta plus gamma is equal to minus b by a and alpha into beta plus beta into gamma plus alpha into gamma is equal to c by a. This is the relationship of the zeros with the coefficients of a cubic polynomial. Find the quadratic polynomial when the sum and product of the zeros is 1 by 4 and minus 1. Let the quadratic polynomial be in its standard form ax square plus bx plus c and its zeros be alpha and beta. The sum of the roots, that is alpha plus beta, is equal to minus b by a, which is equal to 1 by 4. The product of the roots, that is alpha into beta, is equal to c by a, which is equal to minus 1. A quadratic polynomial can be formed from the roots or zeros using the formula p of x is equal to x square minus b by a x plus c by a. That is, p of x is equal to x square minus sum of two zeros x plus product of two zeros. Substituting the known values into this equation, we get p of x is equal to x squared minus 1 by 4x plus minus 1. Simplifying the above equation, we get p of x is equal to 4x squared minus x minus 4. Find the zeros of the polynomial 3x squared minus x minus 4 and verify the relationship between the zeros and their coefficients. The equation 3x squared minus x minus 4 is a quadratic polynomial. Factorizing the polynomial by splitting the middle term, we get 3x squared plus 3x minus 4x minus 4, which is equal to 3x into x plus 1 minus 4 into x plus 1. This can be further written as x plus 1 into 3x minus 4. So, the value of p of x is equal to 3x squared minus x minus 4 is 0 when x plus 1 is equal to 0 or 3x minus 4 is equal to 0. This is when x is equal to minus 1 or when x is equal to 4 by 3. Now, the sum of zeros is equal to minus 1 plus 4 by 3, which on simplification we get 1 by 3. Similarly, the product of zeros is equal to minus 1 into 4 by 3, that is equal to minus 4 by 3. On comparing these values to the given equation, we observe that the sum of zeros is the ratio of negative coefficient of x to the coefficient of x squared. Similarly, the product of zeros is the ratio of constant term to the coefficient of x squared. This verifies the relationship between the zeros and the coefficients of the quadratic polynomial.